platforms if they actually work perfectly for once with no technical flaws whatsoever, like this one. Periscope done. Facebook. Okay, we are live everywhere now, and we have attendees flooding in.
Great. I'm just dropping a tweet.
Right, so welcome everyone to, I don't know how many we've done now, but I think the 8th or 9th Cyber Cafe Sci, the second in our stellar May lineup, so lots of astronomy this month, and slightly less visual and more subtle astronomy this time, with Jenifer Millard of Awesome Astronomy podcast from Cardiff University, and she also writes various articles for sorry, what was the name of the app again? The
Sky
Guide,
available on the App Store.
Yeah. So I highly recommend checking those out. Now, just to do the run through first, there you go, you can see my excellent taste in shirts now. Again, welcome everyone. If you've not attended one of these before, and a large number of you haven't, then if you want to ask a question during the presentation, just drop it in the Q&A or via the chat window, and I will rudely interrupt Jenifer and give her the question to answer. So feel free to do that. We're going to be hearing about millimeter wave.
Wait and see. We're going to be learning about all sorts of stuff.
We're going to find out about the hidden
things.
universe. That's as much as I know about it. I don't know anymore because it's hidden. There is a raise hand button. If you've got any technical issues or technical queries, feel free to do that, or drop me a message in the chat and I'll handle that just offline from the main discussion. Otherwise, I'll hand over to Jenifer now.
Great. So I am just going to move Zoom over to my other screen, and then I'm going to bring up my slides, and then we are going to share screen. Hopefully that's the plan. Let's have a look. Share screen. Okay, great. So I'm hoping that everyone can see a nice slide with the title of the talk and some bunch of information about me. Yes? If I hear silence, I'm going to assume so.
Yes.
Okay.
Yes, we can. You're fine.
Great. So yeah, thank you for the introduction, James. As James mentioned, I am an astrophysicist at Cardiff University, and my research involves studying the hidden universe. So I look at the universe using wavelengths of light that we can't see with our eyes. And that's what I'm going to talk to you a little bit about today, is all the amazing things that we can learn about the universe at these wavelengths. But I don't just do the physics. I also podcast. So it's the Awesome Astronomy podcast that I do. We're everywhere. We're on, Apple Podcasts and Stitcher and Podbean and all those places. 2 episodes a month, one about kind of what's going on in space, and then another one that kind of focuses more on the human side of space exploration. And I also write articles for Sky Guide, as if I wasn't busy enough trying to finish my PhD, which is due in sort of like September time. So yeah, that's fun. Anyway, moving onwards. So hopefully, there we go. In this talk, I'm going to focus kind of on the physical universe rather than sort of the equipment and the telescopes that we use to sort of study the universe, just because of time. We're going to learn all about the electromagnetic spectrum. And we're going to, hopefully, your big takeaway is going to be how important it is to look at the universe using this whole electromagnetic spectrum rather than just the light that we can see with our eyes. So when you look up at the night sky using your own eyes, you might see some of the things that I've got on this slide here. So, for example, you might see constellations. This is a very famous asterism in the constellation of Ursa Major. This is the Plough or the Saucepan, the Big Dipper, whatever you like to call it. You might see some meteors streaking through the sky if there happens to be a meteor shower. We can see things like the moon and the planets. So this is the moon and Venus here. If we're extremely lucky, we might see some comets. We're not being so lucky at the minute when it comes to comets after Comet Atlas broke up when it was slated to be something pretty spectacular. And if you've been to a dark sky site, you might see something like this. So this is a southern hemisphere view of our own galaxy, of the Milky Way. And we're looking here at the core of our Milky Way. And you've got all this, you can see stars, you can see dust, you can see all sorts of things sort of in the sky. This is actually here for anyone who might be interested in some ancient Aboriginal stories. The Aboriginals didn't just have constellations, they also actually used all these dust lanes, these dark patches that we can see in the Milky Way when they were describing what they could see in the night sky. And this is the Great Emu in the sky. So you can see the head here, which is the Coalsack Nebula, and then we've got the body and the tail. So that's what we can see with our eyes. And if you're lucky enough to have maybe a pair of binoculars or a small telescope, then you might be able to see something like this. And here we can start seeing a bit more detail. So we've got some globular clusters here, which are great big balls of stars, all sort of formed together. This is M13. That's what this one's called. And this is just taken through a good amateur telescope. You might start to see galaxies. So this is the Andromeda Galaxy. This is the nearest large galaxy to our own. And then we've got a couple of satellite galaxies here, M110 and M32. You might see some nebulae like this one. This is the Dumbbell Nebula, beautiful blue colors. And here we've got the Orion Nebula in that very famous constellation of Orion. And this is a wonderful sort of stellar nursery where massive stars are being formed right now. But of course, with professional telescopes, because they're so much bigger, they've got, so much more technology sort of embedded into them, we can see so much more. So for example, here we've got the Eagle Nebula. And then if we zoom in on this little box here, we have got the very famous Pillars of Creation. So we can see with professional telescopes so much more than we can see with our own eyes or even with, amateur binoculars, things like that. With M31 again, which is what I showed you in the previous image, here it is, that previous image through sort of an amateur telescope. You can see with the professionals. So this part here is a Hubble Space Telescope. And this here, I can see that there is a Q&A.
So, the Q&A, I'm not sure what that one's about, but there is a question in the
Baker Street Irregulars. Yeah. So I know that people who do the podcast with me they always used to go to a meetup of astronomers in London called the Baker Street Irregular Astronomers. And they meet in one of the parks. I forget which now. So if there is someone, there must be someone here. I can't remember which park it is. Maybe it's Hyde Park, something like that. But they meet and they do some astronomy sort of right in the heart of London. So yeah, something to look forward to if you're a London astronomer. But anyway, sorry, back to the main point.
Yeah, there was one other question, which was...
there's another one.
What is a nebula?
Ah, right. I'm going to come back to that, I promise. That is going to come up later, okay, I will explain that.
I'll remember that and hold you to it. And apparently it's Regent's Park. It's Regent's Park.
Yeah, that's the one. Thank you very much.
And then another question as to whether you can see stars in London.
I think you can see about 3. No, I'm joking. You can see stars. They managed to do quite a bit. Obviously, it's only the brighter things that you're able to see sort of in the heart of London because it's such a big park. It does sort of help with the light pollution and stuff. So, yeah, you can definitely see moon, planets, some brighter things, globular clusters, stuff like that. But I think maybe we can chat to one of the Baker Street Irregulars once the talk's finished, and they'll definitely be able to tell you a little bit more about what you can do at one of their events. So, any more questions before I carry on?
No, just one flippant remark, which I'll ignore.
Okay, fine. So, Professionals, yeah. So this was the sort of view through sort of an amateur telescope. This is something realistic, which you might be able to see with your own eyes. And then with a professional telescope, like Hubble, and also some very, very good amateur kit, which is what this background image is. And then this bit is the bit from Hubble. You know, we can start picking out lots and lots of detail that we just can't see. With the planets, you can see so much more. So this is Saturn. This is a very nice amateur image of Saturn here. And here we've got a wonderful one from Cassini. Obviously, you can see so much more detail in the clouds, and you can see more detail in the rings, things like that. And with the Crab Nebula, which, you know, we are going to come back to, so I will explain what it is. This is an amateur image of the Crab Nebula, but with something like Hubble, we can see so much more detail. We can see all these tendrils of gas and dust and all this really fine structure. But all of those images that I've just shown you, they've been using visible light. So that is light that we can see with our own eyes. And, you know, it's a pretty broad spectrum. It gives us all of the colors, gives us lots of information, but it is just a fraction of all of the light that makes up this electromagnetic spectrum. It's, as you can see, by just looking in the visible, and this range here is, you know, a little bit exaggerated. There's just so much that we're missing out on, right? And that's what we're going to explore in this talk. Now, just because we can only see visible light doesn't mean that all the creatures on this planet are the same. There are actually some that can see some of this invisible light. Bumblebees are one. They can see ultraviolet light. Flower petals are actually very good at reflecting ultraviolet light, and it helps the bees navigate to the flowers that they want to find in particular. Also, snakes, some snakes like rattlesnakes, not all of them, but some snakes can actually sense infrared light. So they don't particularly see it with their eyes, but they have sort of little infrared detectors built into their skulls. So I guess the question is, what is this electromagnetic spectrum, right? Because I've done it again. I've kind of thrown a bit of jargon at you, but I haven't really explained what it is. So what is the electromagnetic spectrum? Well, light is made up of traveling waves, basically. What light is traveling energy. And light is made up of these oscillating electric and magnetic waves. That's what we can see here. And these electric and magnetic waves, they travel at right angles to each other, so they're perpendicular to each other, just like we can see in this little animation here. And all light looks like this. And the difference between light is all about the amount of energy it's carrying. So all light travels at the same speed. It doesn't matter whether it's radio waves, whether it's microwaves, whether it's light that we can see, it all travels at the speed of light. There are a couple of exceptions where light travels through a medium that can change its speed, but we're not going to go down that road because that's a whole other kettle of fish. But broadly, all light is the same, it all travels at the same speed. And what differs different types of light is the frequency that it's oscillating at. And that's dictated by the amount of energy that this light is carrying. So you can see in these animations here that the one on the left is traveling a lot quicker. So it's got a higher frequency. There's a lot more of these oscillations in a given time period compared to the one on the right, where these oscillations are happening quite slowly. If you consider one time period, there's not as many happening at once. So the one on the left would be sort of higher energy light, so maybe something like X-rays, and then the one on the right would be lower energy, so it'd be something like infrared light, something like that. And then when you hear people talk about wavelength, wavelength is just the distance between two peaks, like we can see in these animations here. So this top one here is got a longer wavelength, which means it's a lower frequency. You can see that there's not as many oscillations compared to this one, which means it's lower energy light. And then here we've got lots and lots of oscillations compared to this one, which means it's higher energy. And so it's got a shorter wavelength. Now, as to why the energy of light might differ, well, that depends on the process that produces the light. So if you've got a more energetic event, then you're going to get higher energy light. So you're going to get a higher frequency and a shorter wavelength. So something like this one at the bottom. And then if you've got a less energetic event, you're going to have longer wavelength light, a lower frequency. So something like radio waves, infrared, stuff like that. Now, that's all well and good. Okay. Light is great. But I am sure that you have seen the word photon when you've been reading articles, when you've been, watching YouTube videos about space, and you're like, Jen, this is all great. But what about photons? Where do these come in? Now, unfortunately, to discuss photons, we have to stray into the world of quantum mechanics, which I know is going to have a lot of people looking like this right now. And it's okay, because I promise we're going to do one slide. And this is the slide that when it comes up down the pub in conversation, you can recite this slide and you'll amaze all your friends. It'll be brilliant. Just trust me on it, okay? So, photons, where do they come from? All starts with this guy here, Max Planck, in the 1900s. So he was doing some experiments where he was heating things up and he was measuring how much light they gave off compared to how much light was used to heat them up, because this is how he was sort of imparting the energy to these objects, was basically by directing light in their direction. And according to classical physics, Max Planck should have been able to give as much energy as he liked, and any amount of it, to these things that he was heating up, with no sort of real rules or regulations. But what he found was that he had to have sort of an integer number of these little packets of energy, tiny little packets of energy. So he had to have like a whole number of these little packets. So much like you can have, any amount of money. Some people have any amount of money. I would like to have any amount of money, but you can have any amount of money, but it always has to be made up of whole pennies, right? It's the same concept. So you can have, any amount of energy associated with light, but it has to be made up of these small little packets. And what this means is that the energy involved with light is not continuous. It's not like a piece of string. You can't have, any amount of it. You have to have certain amounts. So instead of it being sort of like a string, it's more like pearls on a string, in the sense of you can't have half a pearl. You've got to have one more or one less. And that's what a photon is. A photon is a packet of light. So there you are. There's your little down the pub explanation of what photons are. So, have we got a question? Is that why my thing has popped up?
Yes. How did he find that out?
He found it out by, honestly, very, very carefully measuring and calculating how much energy he was giving to these objects. So it was very, very sort of precise, careful measurements. Honestly, something that I don't think anyone today would have the patience to do. And just by kind of looking at these numbers, he figured out that he has to have these sort of exact numbers of this tiny little unit of energy fit in. I mean, this unit is how many? A billion noughts, sort of below zero. It's a very, very tiny number. But yeah, it was through very, very careful measurements. And he basically found that the amount of energy was always divisible by this tiny, tiny little energy packet. And so that's where the whole concept of photons come in, is that it has to be sort of these little packets of energy rather than a continuous amount. So yeah, hopefully that answers that question. Okay, great. So now we know what the electromagnetic spectrum is. We know what photons are. We're now going to start our journey through the electromagnetic spectrum. And we're going to start we're not going to go linearly. So we're not going to go from like one end to the other or backwards. We're going to go in the order that they were discovered. So there's a little bit of a history lesson going on as well here today. So if I click here, the place we're going to start is in the infrared. Now, I love the infrared. This is my domain. This is where I do my science, is using long wavelength infrared light, which we'll come to in a little bit. So infrared light, how was it discovered? Honestly, like most of the great discoveries in science, it was by accident. It was by this guy here, Sir William Herschel. Now, what a man he was. He started off his career as a musician, very talented musician. Then decided, I prefer astronomy. I'm going to become an astronomer. He discovered the planet Uranus. He found nebulae, which we will come back to, I promise. He found stars. He also, as if that wasn't enough, discovered the first invisible light. So he started this experiment actually quite for an interesting reason, he started looking at light and looking at the temperature of light because he was worried about climate change. Of all things, yeah, back in 1800s, they were still worried about climate change. And what he was doing was he was using a prism to split up light. So just like this little animation is doing here, he had something very similar to this, and he was splitting the white visible light from the sun into its rainbow of colors. And then he was measuring the temperature of the different colors because he wonders if maybe that had some effect on the climate or something. So what he found is he found that the red light was the hottest and the blue light was the coolest. And he was literally getting some thermometers, just like, you know, you can get very cheaply. And he was sticking them in the different colors and measuring a temperature difference. Now, as any good scientist does, he needed to have a control. So, because he was like, well, is this temperature gradient that I'm seeing, is it because there is actually some temperature difference between these colors? Or is it because there's something funky going on in the room that I'm in? So he thought, right, I'm going to stick what I'm going to call my control thermometer just past the red end of the light spectrum. And lo and behold, to his surprise, he actually measured the highest temperature beyond the red end. So there was something, some form of light that was invisible to his eyes that was actually heating up this thermometer. And what he discovered was infrared light. And when we look in the infrared, that's what we're really looking at. We're kind of looking at heat energy. So at the bottom here, I have got some infrared pictures of bats, and the yellow, white bits are where the temperature is higher, and then the red bit is sort of the coolest. Now, you can actually do Herschel's experiment at home yourself, which is something that I definitely recommend you do. So you can get all the equipment that you need very, very easily. Get an Amazon box, you know, from all the ordering that you've been doing online, which I have definitely been doing while all of this has been going on. Get yourself a prism, a few quid, something like that. These are pennies, the thermometers. And all you need to do is just strap the prism to the side of a cardboard box, just angle it, wiggle it around until you get a nice little rainbow. Strap a few of your thermometers together, and then you can do exactly what Herschel did. So you can see here, this is this experiment. Someone strapped these thermometers together, and you can see that the temperature is highest where there isn't actually any light hitting the thermometer if you compare these. So I really encourage you to have a go at this. It's a really nice, simple experiment, especially if you've got kids at home and you've got to hit their science quota. This is something that you can do. And I think there's another question.
There is. How do you transform IR light to make it visible on a photograph?
Okay, yeah. So it's whenever we detect any sort of light, what we're doing is we're essentially converting that light into an electrical signal. And then we get that electrical signal and then we can transform it, you know, into a picture. So whenever you see pictures of stuff that's in infrared light, it's not necessarily those colors, those will be artificial colors, but it's essentially just turning it into like an electrical signal that we can then see with our eyes. Infrared detectors are a little bit different to normal detectors. So because they don't detect the photons like a normal camera does. Like if you've got a DSLR or something, that thing is detecting photons. Whereas in the infrared, we're detecting heat. So we have to quite often use these detectors called bolometers. And what bolometers do is when there is an incident photon onto a bolometer, it causes a big temperature change in a conductive element in the bolometer, and then that big temperature change is registered as a resistive change, and then that's how we get our electrical signal. So it's all about detecting the temperature change, and that technology requires sort of very sensitive material, often has to be cooled down so that it's not just seeing its own heat, it's seeing the heat of the things that we're trying to find. But yeah, so that's as far as I'm going to go, because I didn't want to talk about the detectors too much in this talk, otherwise we will never get to the end of it.
There is just one, I'm fairly sure, simple question, definitely nothing complex. Is it a linear shift in the frequency?
Oh, that's a really good question.
I promised an easy one.
I would say, is it a linear shift in the frequency? I guess the problem is with all of these things, we have different categories of light, right? So even within the infrared, it's not just infrared light. So there's sort of near infrared and mid infrared and far infrared and submillimeter, and there's all these different sort of subcategories. And I would argue that no, it's not a linear shift in the sense of you can take the sort of limit at where you can stop seeing light right down until we get to the next category of light, which is sort of radio waves and microwaves. And then the categories is like near infrared, mid infrared, far infrared, and not linearly spaced. What we call near infrared, there's a very narrow band which we call near infrared, but far infrared and submillimeter light is a much broader range. But then, that's just by construction. That's just because that's what we've decided where the boundaries lie. It's not because of anything physical. It's just because people are awkward and scientists don't like anything to be simple. So yeah, I hope that answers that question.
Yep, I think so.
So anyway, going back to the experiment, if you do want to do this experiment, this is the link where I got these images from. So if you just type in like cool cosmos and then Herschel experiment, it'll probably come up, and there's a full guide on how to do this properly. So that was the discovery of infrared light in the year 1800 by William Herschel. But in terms of astronomy, it started really slowly with the moon, infrared light from the moon being detected in the 1850s, and then the sun in the 1880s. But in terms of a branch of astronomy, it wasn't really until kind of the 50s and the 60s that we really could do it, just because we didn't have the technology in order to detect the infrared light to the sort of sensitivity levels that we needed in order to get detailed observations, because it requires really quite complex technology. So infrared astronomy really took off when we could also get above the atmosphere, because luckily for us, like the atmosphere blocks out a lot of infrared light from the sun, which is good for life. It's not good for astronomers. They don't like it. So really, in order to detect this infrared light, we had to get above the atmosphere. And that was only really possible when we started having, commercial airplanes that could be used to fly telescopes, or when we could have big balloon experiments, like BLAST. So BLAST is a modern day balloon experiment where they literally attach a telescope to a great big balloon. It flies above Antarctica, and then it crash lands, and then they collect it a few weeks later. And the other thing is that we had to have the technology to sort of cool these detectors so that they can see the heat of the things they're supposed to see and not their own heat. And it wasn't really until the 1980s, actually, that we got our first infrared space telescope, which was called IRAS, which is this one here. So it is actually a pretty new branch of astronomy, I would argue. Now, in terms of things that we've done with infrared astronomy or submillimeter astronomy, kind of collating those two together. When we do infrared astronomy, we're looking at cool things, and quite often we're looking at dust in space. Now, dust in space is not the same as the dust that you get in your house. So the dust in your house is like dead skin cells, bits of fluff, stuff like that. Whereas the dust in space is little fluffy coagulations of rock that kind of look like this. So they can be made of things like carbon and silicon and oxygen, things like that. But they're basically tiny, tiny little rocky particles. And they're everywhere in space. They just kind of pervade the space between stars, a bit like smoke. So you can imagine almost like particles of smoke just kind of all the way through space. But so far apart that you wouldn't be able to see it as smoke. But that's the kind of effect. And then you can get different sized ones. So in our solar system, we have, slightly bigger particles. Maybe they'll be like the width of a human hair as opposed to a fraction of the width of a human hair, something like that. But using infrared astronomy, you can see this is Jupiter in the infrared. And we can see that in the infrared, Jupiter actually has a really, really prominent ring system, which I hope you can see in these images. And that ring system is, unlike Saturn's ring system, which is made up of lumps of ice, this ring system is made up of little dust particles. And, until we look at Jupiter in the infrared, we didn't know that these rings were as prominent as they are. Now, as well with Saturn, we know about Saturn's beautiful icy rings, as what makes Saturn a super popular phenomenon with amateur astronomers. But Saturn also has this great big extended ring of, again, these tiny dust particles. So this tiny little circle in the middle is Saturn, which you can see zoomed in here. And it has this enormous ring of dust around it, which, again, we didn't know about until we had a look at Saturn in the infrared. I will say that this is an infographic rather than a real picture, as opposed to the Jupiter one, which is a real picture. But you get the idea. And what we can do with the infrared light is that, as important as this dust is, which I am going to come on to in a sec, it kind of gets in the way. So this is part of the Eagle Nebula. It's the Pillars of Creation again, which we saw earlier. And a nebula is a big sort of collection of gas and dust, and they can form, in a couple of different ways. So we can have a nebula from a dying star as it's shedding its matter. As when small stars like the sun, when they die, they puff up into these red giants and they kind of slew off all this material. And that can form a nebulae. Sometimes a nebulae is just a great big ball of gas and dust that's out in space. And you can see it glowing because of the energy kind of pouring out from all the stars that are forming in it. That's what a nebula is anyway. And I've seen a couple of questions pop up. Right. So you can tell what you see by its wavelength. Yes, you can. So by looking at things at different wavelengths, it helps us figure out what things are made of, because certain elements we know from experiments in the lab will emit light at certain wavelengths. And if things are invisible at one wavelength, but then are suddenly visible at another wavelength, that can give us information about what we're actually looking at. So that is, another reason why it's so important to look at all these different wavelengths. So yeah, absolutely, you're very correct. And then Sarah Boras, why are they called the Pillars of Creation? Do you know what? I don't know. That is an excellent question. And so I challenge someone to Google that while I carry on with this talk, and then come up with the answer. So
I'll just say personally, I don't know is one of the best answers we ever get out of scientists.
I don't know everything. Why would I pretend?
Answer.
Yeah, why would I pretend to know stuff? That helps no one, I mean, hopefully I'll come out of this talk now knowing why they're called the Pillars of Creation. So yeah, someone Google that for us while I carry on. Anyway, back to the Pillars of Creation. And what we're looking at here is we're looking at them in the visible light. And if we have a look at them instead in using infrared light, we can suddenly see that all this dust that's in the way, it suddenly disappeared. We can see many, many more stars, and we can kind of see right through these pillars, and we can see stars being born. So here you can see there's something hidden. Whereas if we look in the infrared, because the infrared, it just kind of sails straight through that dust, then suddenly we can see another star here popping up. We can see all these stars that we couldn't see before. So it really allows us to study the universe in a completely different way. And there's another question that's popped up. Can I pause the presentation for the NHS?
So generally what we do is when it gets to 8 o'clock, we take a 5-minute break for people who want to clap to go and clap, and everyone else to stretch their legs, grab a drink, and then come back afterwards.
Wicked. There you go. Okay, so yeah, so you can see that we can see the universe looks completely different when we start looking at things in the infrared. Now, where this dust comes from is quite an interesting question, and this dust is produced by dying stars. So I'm not going to talk about this too much because I know that the talk next week is talking all about like supernova explosions and things like that, and this is one of the things that produces dust. So you can tune into the talk next week. But dust is made up of these heavier elements like carbon and silicon. So we can either get them in the really explosive, violent deaths of stars in these supernova explosions where all these heavier elements are fused. or we can get them when these lower mass stars, when they swell up into these red giants, they basically their gravity is not enough to hold on to all the material in their outer edges, and they start puffing off this material. And in this material, they've already got some of the heavier synthesized elements like carbon and oxygen. And as this material puffs away, it cools, and then it can form these tiny little dust grains. So in this picture on the left here, this is the Cassiopeia supernova remnant here in the visible light. And here we can see it again in the infrared, and you can see how much more detail you can see. You can suddenly see all the structure of the dust that's being produced by it, all swept up from the material surrounding it. You can see how brightly the remnant here is glowing in the infrared, which shows that there's a lot of dust in this supernova remnant. And this here is a picture of Betelgeuse, and I'm sure you've all seen a picture of Betelgeuse because of that crazy dimming that it did just back last year. And so this is, the star is right in here, and we can see all these kind of circular layers where material has been puffed off by it as it's swollen up into this supergiant star. And this is the perfect dust factory. I think
we've had a couple. They're not questions. We've had a couple of people answer the pillars of creation. So it's because the gas and dust are in the process of making new stars. So thank you to Avril and Sarah.
Yeah, thank you so much. So I think the best fact about infrared submillimeter astronomy and why it's so important is that half the starlight that has ever been emitted in the entire history of the universe has been absorbed and then re-radiated in the infrared. So if we don't look in the infrared or in the submillimeter, then we are literally missing out on half of the universe, which I think is, pretty astounding. This is probably a very familiar picture to you all. This is the constellation of Orion. It's, really popular. Here we've got Orion's belt. Even if you're not sure what the whole constellation looks like, you should recognize that. And if we have a look at it in the infrared, you can suddenly see all of this glowing gas and dust that we simply can't see in the optical is suddenly revealed. And like was mentioned in the reason for the naming of the pillars of creation, actually, gas and dust is, the building blocks of planets and stars. And this is why studying in the galaxy, the universe in infrared is so important, because we're studying the stuff that we are literally made of. This is what we're made of. We're made of dust. If there was no dust, then the planet that we live on wouldn't exist, and we simply would not exist. This is the Milky Way in the visible light, and then we can have a look at the Milky Way galaxy. So this is our galaxy in the infrared, and suddenly you can see all these details from all the gas and the dust, things like that. And there's another question. Absorbed by what? Absorbed by what? Oh, absorbed. The light has been absorbed, a lot of it by dust, actually. So dust is very, very good at not only blocking out the light from stars, but it actually absorbs it, and then it re-radiates in the infrared. So like Max Planck was doing those experiments where he was putting light onto things, dust is what we call an imperfect absorber. So if it was a perfect absorber, it would all this starlight would be incident on it, and then it would re-radiate it at the same wavelengths. But because dust is not very good at absorbing light, what it does is it absorbs this light and then it heats up a little bit, so it uses up some of that energy, and then it radiates it at a longer wavelength, so in the infrared. And it's in the infrared because it's got a cooler temperature. So yeah, thank you, that was a good point. Carry on. Studying dust allows us, so looking at galaxies in the infrared, studying their dust allows us to figure out, where stars are formed in a galaxy, where there's ongoing star formation, where there's not any stars forming. So this is M31 again. It's the Andromeda galaxy in the visible. This is the Andromeda galaxy in the infrared. And if we line these two pictures up over the top of each other, then we can see where we've got all these dark, dusty lanes. They are actually glowing in the infrared. So we can see here and here, you can see how the dust lanes are suddenly, they're dark and opaque. and they're not much use really in the visible. But then as soon as we look at these longer wavelengths, then we can see the dust and we can study it and we can learn its properties instead of it just, you know, getting in the way. And I think the final thing I want to touch on with infrared and submillimeter astronomy is that when we look at the night sky at these wavelengths, it looks completely different. So this is a picture of a patch of the sky. And these are little kind of zoom in boxes on interesting things. And I'm hoping that you can see in this image, it's full of blobs, right? It's full of all these little tiny dots. And every single blob in this image is not a star, but a galaxy. So just think about that. What might look like a great big field of stars is actually an enormous field of galaxies that we can't see when we look at the sky with our eyes. But when we look at these longer wavelengths, suddenly they are revealed. So we have done infrared astronomy. And the next bit that was discovered in terms of the invisible light was the ultraviolet. And it was actually just a year after Herschel found infrared light. And he inspired Johann Ritter to kind of wonder, well, if there's invisible light at the red end, maybe there's invisible light up at the blue end somewhere. And he discovered it by, again, splitting sunlight up into a spectrum and shining it onto silver chloride paper, which is what they used to use when they did photographic exposures back in 1801. And he found that there was something invisible which was darkening the paper at a quicker rate than the other colours of light were. So that's how ultraviolet light was discovered. And much like infrared astronomy, ultraviolet astronomy couldn't really begin until we could get above the atmosphere because, you know, luckily for us, the atmosphere of Earth is very, very good at filtering out ultraviolet light, which is great because it's very damaging to DNA. So good for people, not great for astronomers. Here we've got the first image of UV light from the sun that was taken by an instrument that was flown on a V2 rocket in 1946. So this was sort of, you know, technology that was captured from the Germans by the Americans at the end of World War II. And this was the first real incident of ultraviolet astronomy. We first started looking at the sun at ultraviolet wavelengths, and then we moved on to other stars with, you know, probes and detectors like this. So we've got the orbiting astronomical observatories and also the orbiting solar observatories that NASA launched back in the 60s. So this is a picture of the sun in visible light. So if you look at the sun with a very specialized telescope, so obviously never look at the sun with your naked eye on its own. If you can look at the sun with a specialized telescope in visible wavelengths, this is the sort of thing that you will see. So these black bits here are sunspots. So these sunspots are just cooler patches on the surface of the sun where there's intense magnetic activity. And in the visible, we can't see this magnetic activity. But if we have a look instead at the ultraviolet, suddenly all this magnetic activity becomes apparent. We can see here, this is gas that's following all the complex magnetic field lines on the surface of the sun. We can suddenly see details in the corona, which is one of the hotter outer layers of the sun, all sorts of detail that we simply can't see at visible wavelengths. And because ultraviolet light is shorter wavelength, we're studying more energetic things now compared to when we were looking at the dust, where it's like a cooler, kind of more steady thing that we were looking at in the infrared. And studying the sun at ultraviolet wavelengths is really important for looking at the origins of solar storms that can disrupt communications and can also damage spacecraft, cause power outages, things like that. And if we look at the other planets, so if we look at planets in our solar system, we can see things like aurorae on Jupiter. So this is an optical image of Jupiter. Over the top, we've got the UV detection of, just like we get the aurora on Earth, we also get them on Jupiter. And these are caused by high energy particles being driven down into sort of the atmosphere of Jupiter by the really strong magnetic field that it has. These high energy particles collide with gas atoms and then cause them to glow, and that's what we see here. Was that a transit of Venus on that UV shot of the sun? Yes, it was, and I purposely didn't mention it because I was wondering if someone was going to bring it up, but yes, you might have spied a black dot on the UV photo of the sun, and that is Venus transiting the surface, transiting the sun as we see it from Earth. So yeah, great spot. Good. I'm glad someone spotted that. So if we look at galaxies in ultraviolet, we can learn about the young, very, very hot, short-lived stars, and where they form compared to sort of the older lived stars. And in this picture of M81, we can see here, this is a visible light image of M81, and this is an ultraviolet image of M81. And we can see in this ultraviolet image that the spiral arms of the galaxy are glowing very, very brightly, whereas the core is really quite dim. And what this tells us is that in the spiral arms is where we've got ongoing star formation. We've got, stars being formed all the time. But because there's a lack of ultraviolet light in the center here, that tells us there's not really any new stars forming because they are older. They're not giving off UV because they're cooler. And so we can learn a lot about how galaxies are structured and things like that by looking in the UV. Oh yeah, I forgot I put this in. This is just to remind you that cooler things down here will be more red, and then the hotter things will, if they're emitting ultraviolet, will appear blue. So that's why we've got that color difference here. So we can look at other galaxies along the bottom in an artificial color. So in the red, we've got visible pictures of galaxies, and then along the top in the blue, we've got the ultraviolet counterparts. So we can see, particularly here for this galaxy, the third one across, it's glowing very brightly in the visible in its core, but when you look at it in the ultraviolet, that core completely disappears. And then suddenly we've got like this bright ring of UV light, which tells us that there's almost like this ring of star formation going on in the galaxy, which is particularly cool. And we can have a look at some more here. So you can see how in the visible light, the centers are pretty bright in these galaxies compared to the UV. They are not as bright at all. And we can see how much brighter these hot young stars are in the spiral arms in the ultraviolet. So ultraviolet done. The next bit we've got are radio waves and microwaves. I'm going to bunch these together because their history is sort of very, very related. So 1801, we've got the discovery of ultraviolet radiation. And then kind of 6 years go by where a lot of very clever physicists do a lot of investigation into these electric and magnetic waves and all sorts of things like that. People that you might recognize, Alessandro Voltage, that's where that word comes from. We've got Michael Faraday, you might have heard of Faraday cages, George Ohm is the unit we use for resistance, and then André-Marie Ampere, and amps is what we use when we're talking about current. But the guy who kind of took all of their work and smashed it all together was James Clerk Maxwell, Scottish physicist, brilliant guy, and he developed what we now call Maxwell's equations.
We've just had a question come in from
Ooh.
George. You said IR was discovered because it was hotter when detected by a thermometer, but UV is hotter in terms of energy. Is that using the term hotter in two different ways?
Yes. So yeah, it's because infrared light is really detecting heat energy, whereas when they're detected in the UVs, the stars themselves are hotter. So yeah, it's sort of talking about two different things, I think. So I'm sorry if that's a little bit confusing. So when we talk about infrared energy, we're talking about sort of heat energy and stuff like that. But when I say UV, we've got these hotter stars. That hotter is referring specifically to the stars themselves. So hotter, younger, bluer stars, that's what I mean by hotter. So they emit a lot of their light predominantly in the ultraviolet. Our star is a kind of midway star, pretty average one, just why it looks yellow. And then you've got cooler, smaller stars, which will look red, and they'll actually emit a lot of their light in the infrared. And the colors that we see in the stars is all to do with their surface temperature. So yes, it is sort of two different things that I'm talking about when I say hotter. So I hope that that's answered the question.
I think so. I think it's just a confusing bit of terminology.
Yeah, it is. There's only so many words for the word hotter. Yeah. But thank you for highlighting it so that I could explain it a bit better. Then back to Maxwell's equations. So James Clerk Maxwell kind of came up with all these equations to describe electromagnetism, and quite interesting things fall out of them. One of them being the speed of light, and that all waves travel at. And the really interesting thing that came out of Maxwell's equations was that there was nothing to limit the wavelength and the frequency of the light, which got astronomers and physicists thinking, because that implies there was a lot more of this invisible light left to find. And find they did. So we're going now to the late 1880s, so quite a jump from when infrared and UV light was discovered. And we got Heinrich Hertz. Here he is. And he did an experiment to generate the first radio waves in the lab. So this is the experiment he had. He produced a voltage, which kind of went up here. We've got these wires here, and they generated a spark. And this produced some electromagnetic waves, which sort of wibbled their way all the way along to this conductor here, this resonator, which then made a spark happen here. Now, because the spark managed to jump essentially from here and here, that was the evidence required to say that there was some sort of invisible light carrying that energy from that first spark to the second one. So he discovered a new form of invisible light, and what he found were radio waves. And he had some pretty interesting things to say about his invisible waves. He said, "I do not think that the wireless waves I've discovered will have any practical application," which we now know it's the complete opposite. And then it was a few years later when Marconi actually developed the first practical radio receivers and transmitters. So it was a long time before we could actually, transmit messages. They were actually more like a Morse code thing when Marconi had his first radio receivers. And then radio for astronomy didn't happen for a long time because of a little thing called World War I. Of course, everyone was distracted by this, and a lot of the investment in terms of the technology went into communication, because that's what the priority was at the time, was developing ways of communicating. And so it's up until the 1930s, when we go to this guy, Karl Jansky, brilliant American radio engineer, and he was hired by Bell Telephone Labs. Now, it is Bell Telephone Labs, as in Alexander Graham Bell, that guy. It is him. And he was hired to fix the problem. Basically, they found that there was a lot of short wavelength interference that was making long-distance telephone calls using radio waves really crackly, and then that was a problem. So they hired Jansky to figure out what was going on. So he built himself an antenna. This is the antenna that he built. It is literally a bunch of wires and sticks that is on a turntable. And interestingly, these wheels are actually from a Model T Ford. So yeah, nice little factoid there. Amazing what you can do with like bits of junk, right? And he was investigating this crackling, and he found that there was a lot of it was due to thunderstorms in the distance. But he did find this kind of faint, repeating background hiss. And it repeated with a period of not 24 hours, but 23 hours, 56 minutes. And that distinction is very important, because if it was 24 hours, then it was probably, something that was moving in the sky. Don't know what, but that's what it would have been. But because it was 4 minutes short of that 24-hour mark, it meant it was something fixed on the background sky. And he consulted some astronomers, and he actually came to the conclusion that the hiss was coming from the direction of Sagittarius, the constellation. And unbeknownst to Karl Jansky, what he'd actually detected was radio emission from the supermassive black hole at the center of our galaxy. Now, Jansky wanted to continue his work because he could see that there was potential for radio waves to really do some cool stuff with astronomy, but Bell Labs went, no, we want to stick with communication, thanks, bye. And that was the end of Jansky's astronomy career. Now, microwaves, I'm also going to talk about, because their development is very closely linked to radio astronomy, because microwaves are essentially sort of higher energy radio waves. And for the first microwaves, we are back at Bell Labs, so 30 years later, and they decidedly changed their mind about astrophysics and the importance of using radio waves to sort of study the universe. And we've got Arno Penzias and Robert Wilson, and they inherited this big horn antenna, this big detector for microwaves, which was originally used to communicate with some satellites. And they wanted to use it to study the radio waves that might exist between galaxies. That was their theory. And they were actually quite frustrated, because no matter what they did, they just detected this sort of hiss, this background hiss. Everywhere they looked on the sky, they couldn't get rid of it. They tried cooling down their detector to see if that would make a difference. They scrubbed the thing to within an inch of its life to get rid of all the pigeon poop and stuff like that on it. But still, there was this background hiss. And what they found, we will come to in a little bit. Now, if we look at planets using radio waves, microwaves, we can see some really interesting things. So this is a picture of Mercury, and it was using radio waves, using radar, that we actually detected polar ice caps on Mercury. So this is a visible image, and this is the radar image of Mercury, and you can see these glowing points at the north and south of the planet. And this is where the ice is reflecting those radio waves back at a much sort of stronger level than the rest of the planet. Venus, when you look at it with the visible, kind of looks like this great big ball of cloud, but with radio waves, we can peer through these clouds and we can suddenly see this really complex topography that the planet has, which we had no idea about. We can see here, so blue bits are lower terrain, and then red and white bits are sort of higher terrain. So we can see all of these mountainous areas and all this really complex stuff going on that we wouldn't see before. So I am keeping an eye on the time, because I know that we need to stop for the clap. If we look at Jupiter in radio, then we certainly detect these really, really strong radiation belts, which are invisible with our eyes, right? So these are visible pictures of Jupiter with then these great big radio lobes either side of the planet. And this is where charged particles are sort of funneled through the very strong magnetic field of Jupiter, and they emit this radiation that we can detect using radio waves. You going up to sort of the microwave end, we can see planet forming rings around stars using microwaves, which I think is super, super cool. So on the left, we've got the pictures of the planets in the optical, of the stars, sorry, in the optical, and you can see you can't see anything around them at all. Whereas if we have a look at them using these microwaves, suddenly we've got all these beautiful ring structures, and the gaps are where the planets are forming. That's what we think anyway. And the one really kind of important thing that was discovered using radio waves was a very special type of star called pulsars. And this is the last thing that I'll talk about before we take that break at 8. And then I will finish the talk. There's not much left after that then. And pulsars are these compact cores left after a star explodes in a supernova explosion. And they are very, very small, the densest material that we know about in the universe. And they have very, very strong magnetic fields, and they sort of channel energy through these jets where these magnetic fields sort of come in and out of the planet. And this lady, Dame Jocelyn Balban et al., she discovered these stars using radio waves. So you can see here, this is the actual data that she took to discover these stars. And you can see all these little blips in her radio data, which is when the beam sweeps across us, planet Earth, as you can see in this little animation here. And that's what she's detecting in the radio waves. So again, looking at this wavelength, if we hadn't done it, we wouldn't know about these really, really exotic stars, which are left over from the deaths of great big stars. So I'm going to stop here because I know that people want to go out and clap, and then I will finish afterwards.
Yep. So if anyone who wants to go and clap, if we come back, let's say 5 past, that's enough time to bang a few pots and pans and grab a drink, and we'll see you then. We may as well leave the pulsar going. I like the animation.
If anyone has any questions, now is a good time to sort of fire them through me, because I will stay here and I will do any extra questions.
So we've got, do the radiation belts cause Jupiter's radio signature in AM 20 megahertz?
Well, that's a really good question. I don't know. Quite possibly. That's what I imagine, because I imagine as a planet itself, the radio emission from Jupiter, sort of ignoring its magnetic field and stuff, is not going to be that prominent. So I imagine that, yeah, if there is a really strong radio signature at 20 megahertz from Jupiter, it's probably going to be from these radiation belts where we've got these particles being accelerated along the magnetic field lines, and then emitting these radio waves. So yeah, that's a great question. So I'm not sure. Maybe.
So probably not high Jupiterian atmosphere radio using jellyfish then.
Oh, wouldn't that be fantastic if it was? And then we just communicate with them by blasting our favourite show tunes.
I think the squid would have to communicate with them. And they say you can hear Jupiter with a shortwave radio, but I never could. That's from Chris as well.
Yeah, I've never tried listening to the planets. I've heard meteors with a radio detector, so you can hear a little kind of, if you set up a radio detector when there's a meteor shower in the correct way, you'd have to have a look at what frequency you need to tune it to, because I'm not sure off the top of my head. But you can hear as they zip through the atmosphere, you can get a little ping on your radio detector, which is quite nice, especially good if there aren't, I can hear people in my studio just started clapping. It's especially good if you can't see the meteors, you can still hear them. So that's a nice thing. And I know a couple of people who have done that. I've never done it myself, but yeah, I know a couple of people who have sort of set up a little radio detector to hear meteors pinging through the atmosphere.
Do you know if any of them have recorded the sound? Just because I'd really love to hear a meteor crashing through the atmosphere.
Do you know what? I reckon if you YouTube it, someone's put it up there somewhere.
I have to put that in the description when this one goes up to record.
Yeah, I imagine that someone somewhere has shoved that up on YouTube.
If not, I'm sure we've got astronomers in the audience at the moment, or will have later, and I know we've got some on the live stream, so please send me the link to the sound, the radio signature of meteors crashing through the atmosphere, please.
Yeah, that'll be great. Nice little outro music to the end of the talk, just some like ping, ping, ping.
See what I can do.
Oh. But I promise there's not too much more left now. We're definitely heading towards the end of the talk. There's just been a lot of good questions, which is nice. It's nice to have an audience that are actually interacting, rather than one that kind of just sits there and sort of, well, normally it stays in silence, but I guess this time it's just kind of watching in silence.
You're likely to, we usually get a wave of questions at the end, so
yeah, that's
you might
fine.
get quite a few.
Yeah, I'm happy with that. That's absolutely fine by me. And, it doesn't necessarily have to be on what I've spoken about. I'm happy to, talk about my research a little bit more. Anything that you've kind of seen in astronomy news that you're like, what's that? I'm a real life astronomer, so you may as well use me while I'm here, right? Take advantage of it. I won't necessarily know the answer to everything, but, I can try. I can do my best anyway.
Speaking of trying, I'm just about to try something, so bear with me. Right, I've just found the sound of meteors crashing through the atmosphere, so I'm going to work out how to stream it into this.
Haha, perfect, great. My GIF has stopped spinning. Is there a timer on GIFs? Didn't think there was. Maybe there is. A certain number of loops before they give up. Any more questions before I get going again? Because it is 5 past now by my reckoning. So I guess unless any more questions come in.
I think you can. Back.
Oh, thanks, Jim. Like that. Jim says, I've really enjoyed your talk. There's a little bit more to go, but we're almost there. So we just need to finish off radio and microwave astronomy. So we've now learnt that we discovered a whole new type of star using radio waves, which we wouldn't have ever found if we were just looking using light that we can see with our eyes.
Here's one. How was Jocelyn Burnell forgotten?
How was she forgotten? Yes, her supervisors were awarded the Nobel Prize, not her, despite her building the antenna that was used to detect these pulsars. It was her supervisors that got the Nobel Prize. However, Jocelyn Bell is not too sad about it because she once, I was listening to something where she was speaking, I can't remember what it was now, but she said, just paraphrasing here, once you win the Nobel Prize, that's it, you don't win anything else. Whereas because she never won the Nobel Prize, she has, been fortunate to be awarded basically every astronomy prize under the sun now. And so she's pretty pleased with that. She's a truly wonderful lady. She won a prize a couple of years ago, and the name of it escapes me, but it was, a couple of £1 million sort of came with it. And she, instead of keeping it for herself, she sort of gave it away for it to be used to allow women and underrepresented minorities in STEM subjects to sort of be able to go and get degrees and pursue, what they want to pursue. Because, when Jocelyn Bell was doing astronomy, there weren't a lot of women around, right? And she is a truly remarkable woman. And if you ever get the chance to sort of speak to her or see a talk by her, I do recommend that you do it. I've met her at a conference once, and she's truly lovely. But yes, I think she's forgotten because it's that time when women in astronomy were not celebrated. It was always the men. But fortunately, times are changing, which is great. So moving on with radio and microwave astronomy. The final thing I want to talk about is detecting sort of gas and things like that with radio astronomy. So using radio astronomy, we can trace the gas from which stars are made using a line which has a wavelength of 21 centimeters. We can detect hydrogen gas. And you can see in these images how much more extended all the gas in this galaxy is compared to where the stars are, which is, completely fascinating, something we would never have known. And this is the way that we actually first mapped the spiral arms of our own galaxy, was using light at this wavelength. Now, for anyone who's interested, this very long wavelength of light comes from when you have a hydrogen atom, so you have a proton and you have an electron. And everything in the universe, including me, is pretty lazy, right? No, they like things low energy. And so what you can have is you have these particles in this hydrogen atom, they have spin, right? So they have, naturally, the lowest energy form of the system is where you've got the proton spinning one way, and then you've got the electron spinning the other way, and they're sort of anti-aligned like this. In comes a photon and it excites the electrons. So certainly they're both spinning the same way. And they don't like this because this requires energy and they're very lazy. So what happens is the electron goes, ugh, and relaxes back down to its laziest form. And when it does that, it releases a photon of light. And that is that 21 centimeter radiation that we're detecting. And this is the first map of the spiral arms in our Milky Way. Now, if anyone's wondering why there's kind of this triangle of blackness at the bottom, that's because the core of our galaxy is so dense that we just can't see through it. So it sort of casts a shadow across the back of our galaxy. So we just cannot detect the radiation at these wave in this part of our galaxy. Another thing that, so while we're on the subject of galaxies, that I just want to mention is that at radio waves, you can find these supermassive jets from these supermassive black holes. So this is an optical picture of galaxy Hercules A. And if we have a look at it at radio wavelengths...
We've just had a question while we're talking about spinning galaxies. Is it literally a spin, as we would think of a spinning top, or is it a name for some other property that just happens to have two states?
It is a different property, which is very abstract, and I don't fully understand myself, because that is the realm of particle physics. But the way you can think about it is like a spinning top. That's how you can kind of conceive it in your brain. But yeah, it's sort of a physical quantum physics property that, as an astronomer, I don't fully understand. But yeah, so you can sort of think about it like that, but it's not really the particle spinning. It's like a property that they have that's called spin. Because why would physicists, name anything straightforward? It's a favorite trait of theirs. But yeah, great question. So, is there another one that's come through?
No, that was a thank you.
Oh, great. So we can get these jets that we can suddenly see when we look at radio waves, like pouring out of either side of these galaxies, that we just wouldn't be able to see in the optical. There's another galaxy here. So this is Centaurus A, truly massive galaxy. And if we have a look at it at radio wavelengths, suddenly we've got another, again, these two great big jets of radio light that's coming out of the supermassive black hole at the center of these galaxies. So the final thing in terms of microwaves is what Penzias and Wilson were looking at, what they had discovered. So when they consulted with astronomers, these astronomers had a theory, and they had a theory called the Big Bang theory. And they figured that if the Big Bang was a real thing, there would be this leftover light from the Big Bang. Only it would be, because it's so old, this light, it would be light emitted 400,000 years after the Big Bang. And it would be so far away that it would be in the radio microwave region of light. And it would kind of be this uniform hiss all across the sky. And this is what Penzias and Wilson, unbeknownst to them, they had found until they consulted with these theoretical astrophysicists. And then, they got awarded the Nobel Prize by accident, almost an accidental discovery. And there's a question.
There is. I was going to wait until you just finished and then start bombarding you with questions. Okay,
yeah, that question, I'm going to get to the end of this and then we'll do that, because this is the radio and the microwaves finished with. So here, as you can see here, the red and the blue, this is a map of our sky from this cosmic microwave background. So the remnant light from the Big Bang, the furthest that we can see back with light, light from the electromagnetic spectrum. This is the furthest that we can go back. And it's this kind of oval shape just because it's a full map of the sky. So I've just kind of shown a map of the world here just so that you can kind of picture in your mind how this might be a full sky sort of map. And this light comes from all directions in the sky. And these tiny, tiny color differences are sort of on the order of hundreds to thousandths of a degree. That's what these color differences mean. And these color differences come from having slightly denser regions and slightly more open regions when this light was emitted. And this light was emitted as the universe cooled. So we had the Big Bang, and the universe was this great big soup of photons of, was a great big soup of photons, protons, electrons, and they were all kind of bumping into each other. And we get to a point that we call recombination, when suddenly these protons and electrons can go together and they can form a hydrogen atom, which is what we see here. And when that happens, all the photons are suddenly free to stream throughout the universe. And that's what we see in this Big Bang light, the CMB, the cosmic microwave background. And where you've got the red, these bits are where atoms were a little bit denser when the light sort of started free streaming, and so then they're a little bit hotter. And then where it's kind of further away, where it's a bit more open, it's reflected then as a temperature change, and the universe was ever so slightly cooler. So yeah, microwave astronomy is pretty cool because you can literally see the oldest light in the universe. And if you tune an old analog radio to between stations, about 2% of that hiss that you hear is this CMB. So also pretty awesome. So that is ultraviolet, infrared, microwaves, and radio left. So we've only got two more now. Gamma rays and X-rays. So the next one is X-rays, and X-rays were discovered right at the end of the 1800s, so 1895, by this guy Wilhelm Röntgen. Look at that beard; that is magnificent. Proper crazy scientist vibe going on here. And he discovered it using a cathode ray tube. So much like when we had the old cathode ray tube TVs, it's the same sort of principle. And what he did is he filled this cathode ray tube with gas, put a voltage to it, made it glow, and then he covered up the tube with black paper. And to his amazement, he could see that there was light passing through this black paper and hitting a screen further away. So he had discovered some light that was so powerful it could pass through solid objects. And, you know, being the crazy scientist that he was, he thought, hey, wife, come here, stick your hand in front of this thing. I want to see what happens because, you know, why not? And so he ended up actually taking the first X-ray, which was of his wife's hand, which is here. So it's a kind of interesting little aside. But X-rays, in terms of astronomy, weren't utilised until almost the 1950s. Because we had to, again, get above the atmosphere. And again, much like ultraviolet, we were looking at the sun. That was the first thing. In the 60s and 70s, we had those balloon experiments like we did with the infrared, and we also used rockets. In the 70s, there was a X-ray experiment put onto Skylab. And then again, just like the infrared, space telescopes in the 1980s. Now, X-ray astronomy is a really powerful tool for studying those supernova remnants that we talked about earlier, those, you know, explosions left over, the leftovers from the explosions of the deaths of the biggest stars. And on the left here, we have got the center of the Crab Nebula, which we've got on the right. So you can kind of see what's on the left here superimposed in the middle. This is the X-ray emission. And what you're seeing here is you can see how the gas and the dust in the nebula is actually being disturbed by the rotation of the pulsar. And this is a real image. This is not, you know, a simulation. This is what we've actually detected over the course of several years using X-rays. We can actually see the gas in the middle of this nebula moving because of the rotation of this star, of this pulsar in the middle. We can also study the accretion disks and the superheated gas that's around the black holes in the center of many galaxies. So we're returning to M81 here, which we had a look at earlier. This is the optical image on the left. And then this is the we've got different wavelengths in the disk. So we've got some infrared light, which is the pink, but in the middle here, this is the X-ray emission, all the blue that you can see. And these are black holes. And here, all the gas surrounding the supermassive black hole at the middle, which is very, very hot, which is why it's emitting at these X-ray wavelengths. We can see here, this is the optical image of a galaxy Cygnus A on the right here, and then we can superimpose the X-ray image over the top, and we can see all this superheated gas again from the black hole at the center of this galaxy. So the final piece of the puzzle is gamma rays. And gamma rays were detected shortly after X-rays, so in 1900, by Paul Villard, this guy here. And he discovered it because he was studying some radioactive material. So it's not as an exciting story as some of the other ones. So even though he discovered the light in 1900, it actually took another 10 years of experimentation and study to confirm that the radiation he was discovering was actually another form of light, just because gamma rays are so powerful that they pass through most solid objects. So it's actually really hard to work with them and figure out what's going on. And again, much like a lot of the astronomy that we talked about, it couldn't really begin until we could get above the atmosphere. So this happened, first of all, in 1961 with the Explorer 11 satellite. They put a gamma ray detector on it. But it was actually an accidental leap forward came in the late 60s, early 70s, when the Cold War between America and Russia was really hotting up. They launched these Vela satellites, and they were to detect gamma ray flashes from nuclear bomb tests. That was the idea. But instead, these detectors were actually finding flashes of gamma rays from deep space. And this is where gamma ray astronomy really comes in. We're looking at really the most exotic high energy systems. So black holes, supernovae, those pulsars, things like that. And also these things called gamma ray bursts, which we don't really know what they are still. They're a bit of a mystery, but they're these very rapid bursts of gamma rays which seem to radiate from somewhere in deep space, and maybe it's from the collision of two black holes, or maybe two neutron stars colliding, or it's something completely different. But we can see here, this is a gamma ray burst on the right at the top, so we can see how it's very, very bright, and then suddenly it fades over time. And then on the left, we've got that Crab Nebula that we've been looking at, so we can see it now at all the different wavelengths. We've got radio, infrared, visible, ultraviolet, X-rays. We can see that pulsar, and again we can see how the pulsar in the center is this really bright gamma ray source. And I've seen a question.
There is, but it's fine.
We'll come back to
bug you
the
about
end.
those later.
Yeah, we'll come back to that at the end. And because gamma rays are so difficult to detect, as you can see in these images, we don't get a lot of detail from them, but they do allow us to study some really exotic stuff. So looking at all the different wavelengths of light, it really does allow us to have a more complete picture of the things that we're looking at. This is M31, the Andromeda Galaxy. We've studied it a lot tonight. But if we look at it together, at all the different wavelengths, suddenly we can see in the radio, we're detecting all that gas. Like when we were mapping the spiral arms of our galaxy, we can see it here in another galaxy. In the infrared, we can see all of the dust. In the visible, we can see the stars, the old ones and the young ones. In the ultraviolet, we can see those really hot young stars. And then in the X-ray, we can study the center of the galaxy and the supermassive black hole there. With our own galaxy, this is our Milky Way. We've seen it before tonight in the visible. And then we can have a look at it again at all these different wavelengths. And then suddenly the picture completely changes. We can see the gas here in the radio at the long wavelengths. In the infrared, we can see dust glowing. In the optical, we can see that dust getting in the way. We can see stars. And then in the X-ray, we can see all this hot gas at the center of our galaxy. And then gamma ray radiation again. Jupiter, remember, in the optical, we can see, the beautiful planet. In the ultraviolet, we can see all those aurorae going on at the top. In the infrared, we can get some really detailed information about how the temperature of the planet is different for the bands and stripes. And then in the radio, we can suddenly see all these lobes that we can't see at other wavelengths. So it really does require us to look and utilize the entire electromagnetic spectrum in order to understand the universe. It really does boil down to that. If we look at the universe, we're just using the light we can see with our eyes, we miss out on so very much. But of course, that is not the full story, right? Light that we can see with our eyes is a tiny fraction of the electromagnetic spectrum, which in of itself is a tiny fraction of what's going on in the universe. So I haven't even touched on gravitational waves, which are a way to study the universe without using light. And also we've got the fact that most of the universe is still hidden after we're using the electromagnetic spectrum, after we're using gravitational waves, because only about 5% of the universe is actually made up of stuff that we can see and we can interact with in one way or another. Another 27% of it is this mysterious dark matter, which we still don't know. And then another 68% of it is dark energy, which we really don't know what that is. So I'll leave a summary up there. These are kind of the big takeaways for you to hopefully have at the end of this talk. And that's it. So thank you very much for quite a long talk, really. It turned out to be in the end. So thank you for sticking by.
The questions do tend to extend it.
Which I didn't factor in.
That's okay. Before we go into the sort of dedicated Q&A, if I just let you get a breather, because I want to try something which is hopefully clever and will work. So if everyone can bear with me for 1 minute.
Yeah, I'm just going to crack my window open because people were shouting outside earlier. It's very warm in here, so I shall be back in a mo.
Okay, so right, if everyone can bear with me, here we go. And for anyone wondering, that was the Perseid meteor as captured by the US Air Force Space Surveillance Radar. So there you go. That's the sound of meteors crashing through the atmosphere for you, which was really eerie and made me think Mysterons. But that's probably a lot about my generation rather than anything else. Okay. Also, before we go into the questions, I just want to say a huge thank you to Jenifer for
That's right, you're very welcome.
doing the talk. It's been great. And I highly recommend everyone go and check out the Awesome Astronomy podcast, as well as if you've got an iPhone, the Sky Guide. And the Awesome Astronomy podcast are on Twitter and Facebook as well, so you can dig them out there. Now, are you ready for some questions? Have you had a moment?
Ready. Let's do it. I've had a few mouthfuls of cider. I'm ready to go. Let's do it.
Right. Have all the forms of invisible light been discovered? Are there other wavelengths off the end of the spectrum which still might be there to be discovered?
That is an excellent question. I think it's really difficult to know whether there is anything further. I think, if anything, we're probably limited by our technology, as particularly kind of at the higher energy wavelengths, because gamma rays and X-rays are so powerful that they sail through solid material, right? So it's really hard to get detectors to work to actually detect anything without the light just kind of sailing through the detectors. So I think particularly at the shorter wavelengths, there's probably areas that we have not explored. Because it's a full spectrum, we've probably only looked at very narrow windows. I mean, X-rays and gamma rays astronomy is not my kind of field. But I believe there's sort of certain windows which we've looked at in detail, but there's probably other windows that we just haven't. In terms of at the radio end, kind of going through to that end, I think, again, probably we've done pretty well with radio astronomy and the longer wavelengths. We've probably found and detected a lot of the light that we know about at those ends. I mean, there's probably longer radio waves that we haven't found because their signals are just so faint and so hard to find. That's what I would go with, and especially it's not something I went into in the talk because it would involve kind of really getting into the nitty-gritty behind detectors and how they work. But generally, when we build a telescope detector, it detects a very narrow range of wavelengths. So there's kind of these little pockets all the way along the continuum of the electromagnetic spectrum that our telescopes and detectors are working at. So I would say that we probably haven't looked at the universe at every wavelength, but we've sampled enough of it to get a good idea, except for probably at the high end, high wavelength, and where we're going to have some issues. So yeah, great question. Thank you, Avril.
Okay, and then I'll come back to that one. Parallel universes can come up in a bit.
Yeah, we'll do that one last, I think.
Why are all of your images of Andromeda at an angle?
Oh, that's a great question. That is because Andromeda is actually angled when we look at it in the sky. So we don't see Andromeda face on. We don't sort of see it as a spiral galaxy like this. It is actually inclined to us at an angle. So off the top of my head, I think the most face on spiral that's pretty near to us is probably M51, which is the Whirlpool galaxy. So that is in Ursa Major, and it's close to the Plough, or the Big Dipper, if you're familiar with that asterism. But yeah, spiral galaxies, when we look at them in the universe, are angled all different ways. So some of them are face on, like the Whirlpool galaxy. Others of them are on the side, like there's one called the Sombrero galaxy, which is like a needle sort of on its side. It's very, very, very thin. But yeah, it's a great question. That's why Andromeda is an angle, because that is how it appears in the sky. And people do a lot of work to do what they call deprojection, so to flatten it out so that they can see really what's going on. And it's very, very difficult to do that if you imagine you're kind of peering through the galaxy, and you've got to peer through all that dust and all that gas and figure out what's going on at the farthest edge to be able to do it. But yeah, it's because it is physically, that's how it looks in the sky. But yeah, great question.
Okay, and do you use false color, mapping the entire spectrum as red, green, blue to view everything as colored?
Yes, definitely. So any images that you see which are outside of the visible wavelength, whatever colors they're in, they're false colors. They are just whatever the astronomer who made the images wanted the colors to be. Usually in the infrared, people tend to use red if it's 7mm infrared, because we're looking at heat. So that kind of connects quite well with anyone who's looking at it. And then hotter wavelengths, that's not correct. A shorter wavelengths, when we're looking at hotter things, it tends to sort of be blue colors that astronomers will go for. But yeah, particularly if people are looking at an object at 3 different wavelengths in the infrared, say, they will pick, like you said, a green, a red, and a blue, just to represent the different wavelengths. But it's nothing physical, those colors. It's just whatever they happen to want to use. But yeah, good question.
And I'll come back to the dark matter one as well. Many thanks for a fascinating talk. Could you please tell me where I could find out more information?
Oh, thank you very much, Jim. I'm glad you enjoyed it. More information. The NASA websites are very, very good for this sort of thing. Also, Caltech, their website has got a lot on there. You can listen to my podcast as well, just to do a little plug. But there's 3 of us that present the podcast, and we're doing a segment at the minute called the electromagnetic spectrum, where I'm going through each area of the electromagnetic spectrum in detail, each episode. So I'm doing it at a little bit more finer detail than I am in this talk. And so in the first episode, we're talking all about the actual science behind it, the physical things that we can study at these wavelengths, which is kind of what this talk focused on. And then in the second episode, we talk more about the instruments, the people behind the discoveries, and things like that. So yeah, you can listen to my podcast, but also NASA and Caltech have a lot of information on this sort of thing.
And are there stars out there that are so redshifted that they are only visible in infrared? And will we be able to see them with the James Watt telescope?
Right, that is a great question. So in terms of stars, not stars specifically, but galaxies, yes, because every star that we sort of see in the night sky, all those stars belong to our own galaxy. We can detect other stars in other galaxies, but only very nearby ones. So like the Magellanic Clouds, which are satellite dwarf galaxies of the Milky Way, we can find individual stars in those. We can find individual stars in M31, but beyond that, everything is too far away, and it has to sort of be balls of stars and things like that we can see. However, there are absolutely galaxies which are so redshifted, they're so far away from us that they are invisible to us in optical light, in the light that we can see. So particularly, there are these really bright galaxies. There are submillimeter galaxies, which they get their name because they're really, really bright at submillimeter wavelengths. But quite often they don't have any visible counterpart, and that is because these galaxies are so dusty that a lot of their optical light is obscured, and it's radiates in this infrared, in this submillimeter light. There are also galaxies that are just so far away in the early universe that we can't see them in the visible. We can only see them at longer wavelengths. So I think one of the earliest galaxies we found is sort of about redshift 10, which is about 1 billion years after the Big Bang, I think, something like that, which is truly astonishing to have, a fully fledged galaxy at that sort of time in the development of the universe. But there are also galaxies which are called ULIRGs, which are ultra luminous infrared galaxies, which are super bright in the infrared. And will we be able to see them with the James Webb telescope? Then yes, that's one of the things that James Webb is going to do, is have a look at some of the earliest galaxies and detect them, hopefully, fingers crossed. So yeah, excellent.
And Alistair's just asked one that I asked you earlier. What's your backdrop?
Oh, I was so hoping someone was going to ask about this. Yes, it is actually the control panel for the AAT, the Anglo-Australian Telescope, down in Australia, unsurprisingly from the name. So I visited this telescope about 5 years ago when I was doing a trip there. I was working there for the summer for about 13 weeks. And we got to do a trip up to the observatory, which is in Siding Springs. So it's about a 7-hour drive north of Sydney. That's where we're talking about in Australia. I was there when New Horizons made its closest approach to Pluto. So that's my fun little fact about that. But yeah, it was built in the 70s. So it is it's very eclectic retro dials, very clunky and satisfying buttons. I guess they've upgraded some of the monitor screens maybe over time. I can't really recall. I was very excited about seeing New Horizons data and stuff sort of sailing by. But yeah, that's what it is. I figured it would be good to have a non-copyright background so that people can't shout at me for using it. So yeah, that's what it is. Control panel of a 4-meter telescope in Australia.
Okay, and then we've got the last two difficult ones, but Alistair has just said you never mention your backdrop on the podcast.
This is a long-running joke about the fact that I never bring up the fact that I went to Australia on the podcast. Only I always bring up the fact that I went to Australia on the podcast. So it is this long-running joke from listeners, long-time listeners on the podcast. Well,
I'm glad we've got some of your listeners on, and I hope they've enjoyed it. Right, let's go with the interesting ones. Let's start with the dark matter. Do you think we can see dark matter, and I suppose that's ever see dark matter, in a meaningful sense?
Well, we will never detect it with electromagnetic radiation. That's why it's called dark matter. Because literally, for once, astronomers have named something reasonably sensibly, because they never do. But they call it dark matter because it's dark in the sense of it doesn't emit any sort of light. So if we're going to see it, we're going to see it in a different way. So we're going to see it by detecting some kind of subatomic particle from it. However, that doesn't mean that we won't be able to see it with our eyes, because what we'll do is we'll do what we always do with these images at different wavelengths, where we'll convert it into something that we can see with our eyes. So, we'll take these detections, we'll convert them into an electric signal, and we'll convert that electric signal into a picture that we can then kind of compute within our brain. Because particularly like these great big radio jets out of galaxies, it's really, really kind of hard to imagine this invisible radiation that's so powerful coming out of the middle of these galaxies. So yeah, we'll do something like that. That's what we'll do. So we will sort of see it, because we'll artificially allow ourselves to see it.
And an expansion on that one also from Chris, and I think this was answered actually with the meteor sound, but we always visualize, is there value also in making sound we can hear?
Absolutely. So people have done this recently with so stars, they have these resonances inside them, and they kind of pulsate a little bit. And so what people have done is they've measured the sort of frequency that these pulsations happen at, and they've turned them into sound so you can actually hear it. So yeah, I think there is absolutely value in sound, and also like using all of our other senses to be able to explore the universe. So I've come across, when I've been at fairs and events, where people have 3D printed the solar system, for example, or they've 3D printed a nebula, and you can feel all the different bumps and stuff where you've got all these gases and stuff. Because I think what we often forget in astronomy is that because so often we view these objects as 2D images, they look like flat objects, but they're not. Everything has this 3D structure. And now we're starting to get videos where you can fly through the Orion Nebula, for example, because we can get enough detail that we can figure out that something is slightly further away from us or something is slightly closer to us, so we can get that little bits of detail. But I think there is truly value in kind of expressing what's in the universe through other mediums. But yeah, listening to stars is a pretty cool one. And you can listen to the CMB, don't forget, if you tune your radio between stations. Yeah.
Okay, and finally, and I'm pretty sure this is from his Dark Materials, but I did see the headline earlier, about the Antarctic neutrino detector in the parallel universe.
Yes, so this is a news story that broke very recently, yesterday or today, about have we detected a parallel universe? And what the detection is that this neutrino detector has found these neutrinos, which are seemingly coming from the middle of the Earth. and we don't really know why. But I think the problem is that the headline has been jumped on and the wrong interpretation has been taken. It's this classic thing where the astronomers have been like, well, these particles that we're detecting don't really fit with the model of the universe that we have. It could be because our measurement is wrong, or it could be because there's this parallel universe. And the measurement being wrong is not exciting. A parallel universe is very exciting. So I think what's happened is all the news stations have kind of jumped onto this, oh, we found a parallel universe, whereas actually what's happened is the scientists have found something really weird. They've published their work, as they should, saying, hey, we don't quite understand what this signal is, but we found something really weird. What does everyone else think? And it's being construed as this parallel universe, whereas in all likelihood, it probably isn't. I mean, it could be. Never say never, right, when it comes to astronomy, and especially with neutrino astronomy, because we don't know a lot about it. But I think, unfortunately, I'm really sorry to disappoint Chris, but it's probably not a parallel universe. It's probably just something strange.
Okay, and just a tiny bit more on the neutrinos, and I think this is probably the last one. They detect radio from neutrinos passing through ice. And then there's an accusation that you're a spoilsport for
I am a
saying it's
spoilsport. I'm so
unlikely
sorry.
there's a parallel universe behind
I know,
it all.
I'm so sorry. I'm so sorry. I mean, I'm not saying that there is no parallel universe. I'm just saying it's probably we haven't detected it right now. But yeah, so neutrinos passing through ice. Yeah, so they like to bury the neutrino detectors deep beneath the earth, beneath mountains, beneath ice. Why not? So that they can kind of isolate the system from anything that might disturb the experiment. So any to kind of filter the neutrinos through a little bit. And what they do is they have these like maybe bubbles or tanks sort of full of a particular material, like xenon, something like that, something very heavy atom, so that when a neutrino sort of smacks into it, we can detect that that motion. You want something heavy so that it's got at least a chance of kind of stopping the neutrino a little bit, whereas if you've got something lightly, the neutrino is just going to blitz through it. It's almost like trying to stop a bullet with a piece of paper or trying to stop a bullet with a chunk of lead. Is that sort of idea. But yeah, they do bury these things deep underground, and they wait for a neutrino to bump into the nucleus of a very heavy atom. And it doesn't happen very often because neutrinos are notorious for not interacting with matter very much. They just kind of sail through. But yeah, that's how the experiments work.
Okay, thank you. We've not got any other questions, so I will talk on quickly before we get any more. Just a huge thank you. That was absolutely fascinating. I know there's a lot of compliments popping up in the Q&A now, so obviously everyone else enjoyed it. Unfortunately, with a virtual event, it's very hard to do applause, but occasionally people rapidly click and unclick the raise hand button, which looks a bit like applause. Speaker. So that's an option. If this was a normal cafe sci, we would say if anyone wants to buy the speaker a drink, please go ahead. But instead, again, as that's not an option, we'll just say that cider you're drinking was from us and count that as a thank you. But if you do want to check out the podcast and hear more from Jeni, please jump over to Awesome Astronomy Pod. It is good. I've been Awesome Astronomy Podcast, not just Awesome Astronomy Pod, but it is good. I've been catching up on it when I've got the time to.
Yeah, I mean, also, if you think of any questions once we're finished here tonight, then you can fire them over to, at Awesome Astropod on Twitter, or myself on Twitter. I'm just at Jeni Millard. I'm pretty easy to find on there. Or you can email the podcast, which is the show at awesomeastronomy.com. Or send your questions into James, because James is going to fire over any questions people might think of afterwards, I guess, right?
Yep, I will send them over. I'll tag the podcast with them and tell people to go and listen to the next episode where you'll answer them.
Yes, yeah, exactly, because we're recording on the 29th, so yeah, got a good week to get any questions in, and then we release on the 1st and the 14th or the 15th then of the month.
Okay, so there you go. You've got a week to get the questions in one way or another.
Mhm.
And just our selfish bit, next week we've got more on stars, and it's Eloise Stevens, all the way from New Zealand, and we're not flying her out. It's going to be an online session. We're going to be running a bit later than normal, partly so that she doesn't have to get up extremely early in the morning, and partly because it will mean that we're running at 9 o'clock, and if you want to, you can go out and sit and watch the stars while you're watching the podcast. And she will be talking about exploding stars and core collapse, which I am assured is more about stars and not about what's happened to my fitness since I've been spending so long at a
Oh,
desk.
so true.
We also have just so it's not a purely astronomy month, we do actually have a special edition at 5 o'clock on Saturday the 30th, where we've got Jada Elcock, again, international speaker, talking about sharks. So we've got a Shark Saturday. The name Shark Week was taken, so we've just got the Shark Day, but she is extremely passionate about sharks, knows a lot about them. I highly recommend it. It's going to be fascinating, and while everyone loves astronomy, it will be a break from crooking your neck up at the sky so much. So thank you again, Jeni.
Thank you for having me. It's been great.
It's been fantastic, and we've loved having you here. And I'm going to end the call now. So thank you to the attendees as well.